Hey StudyBuds, I'm your StudyBud Hannah, and in today's tutorial video, we are going to discuss a new topic which is about plate theories and boundaries. First up, we are going to discuss the three plate theories which are the following: the plate tectonics theory, the continental drift theory, and the seafloor spreading theory. Plate tectonics is the theory that the Earth's outer layer is divided into several plates that glide over the mantle. These plates act like a hard, rigid shell. The strong outer layer, called lithosphere, includes the crust and outer part of the mantle. Below the lithosphere is the asthenosphere, which is malleable or partially malleable, allowing the lithosphere to move around. Now, let us know what are the plates in this theory. First, we have the North American plate, then the Pacific plate, the Eurasian plate, the African plate, the Indo-Australian plate, Australian plate, Indian plate, South American plate, and last but not the least, the Antarctic plate. The largest among these 9 plates is the Pacific plate at 103 square kilometers. Most part of this plate is located under the ocean and is moving at a pace of 2.5 inches per year. The next theory that we are going to discuss is the widely known continental drift theory. This theory states that the continental land masses were once part of an enormous supercontinent called Pangaea and then slowly drifted apart. Here are the following evidences that support this theory. First is the discovery of identical rocks of the same type and age on both sides of the Atlantic Ocean. Next, ancient fossils of the same species of extinct plants and animals are found in rocks of the same age but are on continents that are now widely separated. Another evidence was the magnetic polarity on the same continent with rocks of different ages. Also, the edges of the continents on the map seem to fit together like a jigsaw puzzle. Now that we're done with the continental drift theory, let's now move on to the seafloor spreading theory. The seafloor spreading theory states that oceanic crust forms along submarine mountain zones, known collectively as the mid-ocean ridge system, and spreads out laterally away from them. The following evidences support the seafloor spreading theory. First is the evidence found from molten material. Scientists identified strange rocks shaped like pillows or like toothpaste squeezed from a tube. These only form when molten materials underwater harden quickly. Thus, these are indicators that molten materials have erupted repeatedly along the mid-ocean ridges. The next is evidence from magnetic stripes. Scientists discovered that rocks found along the ocean floor contains iron. These rocks began as molten material which cooled and hardened. As they underwent the process of cooling, the iron bits inside lined up in the direction of Earth's magnetic poles. This process locked the iron bits of rocks in place, giving them a permanent magnetic memory. Last is the evidence from drilling samples. Samples from the seafloor were brought up through the pipes. Then, the age of the rocks were determined by scientists. They concluded that the farther the distance of the rock from the ridge, the older it is. The youngest rocks were always in the center of the ridges. This showed that the seafloor spreading really has taken place. And that's it for plate theories. Now, let's discuss the plate boundaries. Plate boundaries are the edges where two plates meet. Most geologic activities, including volcanoes, earthquakes, and mountain building, take place at plate boundaries. It is composed of two distinctly different types of material: the less dense continental crust and the more dense oceanic crust. Geologists have hypothesized that the movement of tectonic plates is related to convection currents in the Earth's mantle, which is driven by the radioactive decay in the core. With the Earth's solid crust as a heat insulator for the hot interior of the planet, the magma in the mantle causes tremendous heat and pressure within the Earth, causing it to flow in the convection currents. These currents result to the movement of the tectonic plates that make up the Earth's crust. The first plate boundary that we are going to discuss is the divergent plate boundaries. This is the plate boundary where two plates move away from each other. Oceanic. When a divergent boundary occurs beneath the oceanic lithosphere, the rising convection current below lifts the lithosphere, producing a mid-ocean ridge. Extensional forces stretch the lithosphere and produce a deep fissure. When the fissure opens, the pressure is reduced on the superheated mantle material below. It responds by melting, and the new magma flows into the fissure. The magma then solidifies, and the process repeats itself. Effects that are found at the divergent boundary between oceanic plates include: number 1, a submarine mountain range such as the Mid-Atlantic Ridge; number 2, volcanic activity in the form of fissure eruptions; number 3, shallow earthquake activity; number 4, creation of new seafloor; and number 5, a widening ocean basin. Continental. Its effects. A rift valley sometimes occupied by long linear lakes or a shallow arm of the ocean. Numerous normal faults bounding a central rift valley. Shallow earthquake activity along the normal faults. Volcanic activity sometimes occurs within the rift. Convergent plate boundaries. This is where two plates are moving toward each other. One plate eventually slides beneath the other, causing a process known as subduction. This plate boundary has three types, depending on the type of crust present on either side of the boundary: oceanic or continental. These are ocean-ocean, ocean-continent, and continent-continent. Oceanic and oceanic. In collisions between two oceanic plates, the cooler, denser oceanic lithosphere sinks beneath the warmer, less dense oceanic lithosphere. As the slab sinks deeper into the mantle, it releases water from dehydration of hydrous minerals in the oceanic crust. This water reduces the melting temperature of rocks in the asthenosphere and causes partial melting. Partial melt will travel up through the asthenosphere, eventually reach the surface and form volcanic island arcs. Continental and oceanic. The oceanic plate subducts into a trench, resulting in earthquakes. Melting of mantle material creates volcanoes at the subduction zone. Continental and continental. Continental lithosphere is too buoyant to subduct deeply, so rather than a subduction zone and trench, these boundaries encompass a thick mess of folded, piled-up crust. This compression results in massive mountain belts rather than the volcanic arcs powered by subduction zone magma in the other two cases. Lastly, we have the transform plate boundaries where the two plates slip past each other. At transform boundaries, lithosphere is neither created nor destroyed. Many transform boundaries are found on the seafloor where they connect segments of diverging mid-ocean ridges. Places where these breaks occur are called faults. California's San Andreas Fault is an example of a transform boundary. And that's it for today's video, StudyBud. Hope you learned something new today. See you on the next one!